Welcome back. Today's discussion is about writing conditionals and loops in MIPS assembly language. First, let's look at the memory map in MIPS. The .text section for code is at the top of the map in the lowest memory addresses. Next comes the .data section for static data. Notice that the largest portion of memory is for the stack and dynamic data. Dynamic data is allocated at runtime. For example, in Java, when you use the new keyword, you're allocating memory dynamically. Dynamic data is often called the heap. At the bottom of the memory and growing upwards is the stack. We'll use the stack in some of our function calls. Notice that the stack and dynamic data are growing towards each other. So far, our programs have proceeded sequentially through the code in a fetch, decode, execute cycle. The next instruction is fetched from memory, then it's decoded similarly to what we've done manually, then it's executed by the ALU, and then the PC register is updated to point to the next instruction. The PC program counter is one of the 32 general purpose registers that is always pointing to the next instruction to be executed. As you single step through a program, you'll notice that the PC is updated by 4 after each instruction is executed. That's because an instruction is a word or 4 bytes of memory. Notice here that the PC is 004000C, which is the highlighted instruction that is about to be executed. Assembly languages don't have abstract control structures like if statements or while loops. Instead, we build these structures from simple branch and jump instructions, which are basically like go-to statements. There are 2 MIPS branch instructions, BEQ and BNE. Branch equal will compare 2 registers, RS and RT, and branch to label if they are equal. Branch not equal will compare RS and RT, and branch if they are not equal. Notice that these are conditional jumps. If the condition is not true, the branch will not be taken and the next instruction after the branch will be executed. Whereas branches are conditional jumps, the JLabel instruction is an unconditional jump. The way this is achieved is that the current value of the PC is replaced by the address of label. How do we use branches and jumps to implement an if statement? The flowchart and the C code show that if I equals J, the add is executed, otherwise the subtract is executed. The way we implement this in MIPS is to branch based on the opposite of the conditional. That is, instead of checking that I equals J, we check that I does not equal J. And if that's true, we branch to the else. If it's not true, meaning that I really does equal J, we fall through to the add. Then in order to not fall into the else clause, we have to jump over it. This seems like a backward approach at first, but if you study the logic, you'll see that it's the most efficient way to implement the if-then statement. Let's go over that one more time. If I equals J, we want to do the add. If I does not equal J, we want to do the subtract. This is the same code, but put in the context of a complete program. So one more time, notice that S3 and S4, these represent I and J. And if they're equal, then this branch will not be true and we'll do the add, and then jump over the else. If I and J are not equal, then we'll jump to the else and do the subtract. Let's look at how this is assembled. We see the branch statement here, and we see that it assembled into 2. That's because the PC is already pointing to line 19, so the else will be 2 instructions, 2 words below that. Notice that the jump is unconditional. When we say jump exit, it assembles into J and then the actual address of the exit. We've seen previously that the I format was used for load word and store word, as well as the immediate form of arithmetic and logic instructions. The I format is also used for branches. So we'll have our opcode in the first 6 bits, and we're comparing RS and RT for both branch equal and branch not equal. And then we have our offset, which will be in words in a 16-bit location. And this offset is going to be relative to the current value of the PC, which will already be pointing to the instruction below the branch. To summarize the differences between a branch and a jump is unconditional, and the PC will be updated to point to that label. And the jump can go anywhere in the code segment. A branch is conditional, and it's relative to the current value of the PC. The 16-bit offset that's added to the PC can be positive or negative, meaning we can have both forward or backward branches. MIPS only has these 3 instruction formats, R, I, and J. We've seen R and I quite a bit. Next we'll look at J. The J instruction format, like all 3 formats, has 6 bits for the opcode. And that leaves 26 bits for the label. But addresses are 32 bits, so how does that work? At runtime, the 26-bit address is shifted left twice to become 28 bits. That puts 2 zeros on the end of the address. Then the upper 4 bits of the PC are appended to the most significant bits of the address. Let's look at a couple of examples of using branches and jumps to implement loops. This example is a counterstyle loop, similar to the while loop that you see here. So while I is less than 3, we're just going to increment I. T1 is set up as I, and T2 will be our stopping value. At the top of the loop, just like a real while loop, we check to see if our condition is met. In other words, is I equal 3? If that's true, we're finished and we'll jump out of the loop. If it's not true, we'll add 1 to I and jump back to the loop. So we'll stay in this loop right here until I equals J. This program shows how to iterate through an array. So we have a small array of 3 words, with the final and 4th word here being a sentinel value, meaning the end of the array. In this program, we'll let S3 equals I, and it will start off at 0. S6 is going to hold the base address of the array, which is the same as the address of the first element. And S5 is our sentinel value. First, what we do is shift left logical I 2 times. That's the same as multiplying I times 4. Then we add that to the base address of the array. So T1 will now be a pointer to the next array element. We load that array element into T0 and branch if it equals the sentinel value. If it doesn't, we add 1 to I and continue looping. Let's see what these programs look like in MIPS. This is our while loop, a counting loop, which just really shows the structure of a loop. It's not really doing anything. So if you wanted to actually have a body of the loop, you would put it in here. So let's just see the mechanics of this loop. We're going to put 0 into T1 and our stopping condition in into T2. At the top of our loop, T1 is 0, T2 is 3, so we're not done yet. We'll fall into the loop, add 1 to T1, and jump back up to the top. Now T1 is 1, it's still not 3, so we'll fall into the loop again, add 1, jump back up. T1 is now 2, still not 3, so we add 1, jump back up. Now T1 is 3, and we'll jump out of the loop. Now let's look at our second loop example where we're looping through the array. We see here in memory our 3, 8, and 12, and then our sentinel values in the array. We're going to let S3 be I, so that starts off at 0, and S6 is the base address of the array. S5 will hold the sentinel value. At the top of the loop, we multiply I by 4 with SLL, so keep in mind that the first time through, I is 0, so when you multiply it by 4, it's still 0. And then when we add the base address of the array, T1 will be pointing to the first array element. The first array element is loaded into T0, and we see that T0 contains 3. That's not equal to our sentinel value, so we add 1 to I and jump back up to the top of the loop. Now I is 1. And when we multiply it by 4 with the SLL, I will be 4. Add that to the base address of the array, and we're now pointing to the second word. We load that second word into T0, which is 8, and it's still not equal to our sentinel value, so we add 1 and jump back up. We'll do that one more time. Now we loaded the last array element, 12. One more time. Now we loaded the -1 into T0, and we will jump out of the loop. The two branch statements, branch equal and branch not equal, give us binary choices. What if we want to implement something like less than or equal to? In MIPS, we implement relational conditions by combining the branch with a set instruction. Set less than instruction will set the destination register to 1 if the two source registers are in a less than relationship. Otherwise, the destination register will be 0. There's also an immediate version. Although there's only the set less than, you can implement any relational condition by swapping the order of the source operands. We also have a lot of pseudo instructions for branches. You can implement code like branch less than equal to, branch greater than or equal to, and so forth. And MIPS will assemble these into pairs of SLT and BNE or BEQ instructions. In my opinion, this makes the code much more readable. Next, we discuss how to implement functions in MIPS. Different languages may prefer the terms functions, procedures, or subroutines, but in assembly language, we're going to use these terms interchangeably. There's some things we need to do in the calling code before we call the function. There's some things we need to do in the function, and then there's some steps we need to take after the function's called. In the calling code, we're going to place any data that we want our function to know about in registers A0 through A3. And then we're going to jump to that procedure. Then the procedure will push things on the stack if necessary, do whatever the procedure or function was designed to do, and then place any results it wants the calling code to know about in registers V0 and V1, and then jump back to where it was called. The calling code will now have its return values in any of the V registers V0 or V1, and it can handle those as appropriate. There are several conventions for register usage in functions. The calling code will put data it wants the function to know about in A0 through A3. The function will put data it wants the calling code to know about in V0 and V1. Up to now, we've been using the T and S registers interchangeably. But the convention is that using a T register in a function is fair game. In other words, a function doesn't have to worry about overriding the values in the T registers. It's the responsibility of the function code to make sure that values in S registers are preserved across the function call. It can do this by pushing them onto the stack at the top of the function. We'll learn how to use the stack and the stack pointer later. the frame pointer and global pointer are not important in our Mars IDE, so I won't discuss them now. To implement functions, we need to learn two new jump instructions, one to jump to the function and one to jump back from it. To call a function, we use the JAL jump and link instruction. First, it saves the value of the PC to register RA for return address, so we can get back, and then it jumps to the procedure label. Keep in mind that as we're executing the jump and link, the PC is already pointing to the next instruction after the jump and link, and that's where we want to return to. The very last statement in a function will be JRRA for jump register. This will copy the value that was stored in the return address, register RA, to the PC so that the next instruction to be executed is the one immediately after the jump and link. Let's look at a simple function in MIPS. A leaf function is a function that doesn't call any other function and doesn't call itself recursively, so it's the simplest type of function. We see the function code here down below our main program, below our exit. Some documentation at the top of the function explains what it does. Let's look at the calling code first. We load into A0 and A1 the two arguments we want our function to know about. Then we jump and link to the function. This function will sum those two values and put the result in V0, and then finally jumping back after the jump and link. V0 contains the sum of x and y, which we can store. Let's look at that in a demo. There's a lot of jumping around here, so let's see how that works in the function. I'm going to assemble this, and then I'd like to skip down to where the function is called. Alright, so we've skipped over the part where x and y are loaded into A0, but you can see that over here we have 3 in A0 and 5 in A1. Now we're going to jump and link to sum. Let's look at the current value of our PC. It's 400010, and our RA currently has nothing in it. If I single step into the jump and link, what we notice is that the RA has been updated to 400014, which is the statement after the jump and link here. And the PC is now pointing to the first executable line of code in the function. This function only has one line of importance here, which is adding the two values and putting the result in V0. And we see that we added 3 and 5 and we got 8. Now we execute the JRRA. Notice the JRRA copied that value that was saved in RA back to the PC. And when we get back to our main calling code, V0 still holds our result, which we can store out to memory here. So there's a few things to keep in mind. These conventions of the A registers and the V registers, they're conventions. We can casually say in speech that we're sending A0 and A1 to the sum function, and we can say that the sum function returned V0, but there really wasn't any sending and returning. It's just that the main program and the function are looking at the same set of registers. In this video, we learned how to make much more interesting programs. We can write if-style conditionals, loops, and functions. There's a set of starter programs in Piazza that you should code up and run before the next class. We'll discuss them in class. The material in this video can be easy to listen to, but then hard to implement when you sit down to code. It's like the difference between watching somebody ride a bicycle and actually getting on the bicycle and riding it yourself. For that reason, I strongly encourage you to download and code up these programs. Until next time, happy coding!